So now let's talk about CDF. I will create plots first, and then I will explain how to use CDF for some calculations of the intervals, and in this case for the probabilities. Okay, so CDF. We will use the same X that we generated before, but now we just need to generate the probabilities for this X values. So in this case we use P norm for normal distribution, so X, and then parameters mu and sigma. And then we use P unif for the uniform distribution, and then I need to use the same parameters, -3 times sigma, it's a minimum value, the smallest value, and mu plus 3 times sigma for the largest value. Okay, then I will do the same in this case. I will create a plot with two curves. So first I create a plot for the normal distribution f1, then I say it's a line plot, and then the color should be blue. And the main title is CDF, cumulative distribution function. Then I will add lines to this plot, x, f2, then the color is red, okay. And then I will just copy this legend, because the legend will be the same, so I will just copy it here. And the only thing I will change, I will use it top left, because the right part will be occupied, so to speak, by this line, so I will just use top left for the location of this legend. Now I can calculate do the calculations and plots. So that's the CDF functions. Okay, so this is the value, and this is the probability to get a value equal or below given. Okay, for example, you can see that for the 70, if you take 70, okay, let me add some lines here. So AB line, the vertical line, which is equal to 70, okay, and then I will make it a dashed line. And then I will also add a horizontal line, which will be equal to 0.5, which is the average, the median. So h equal to 0.5, LTY equal to 2. Okay. So if I run this now, I can get the lines, so you can see exactly that this is where these two functions intersect. And of course, in both functions, for both distributions and uniform distribution and normal distribution, they are both symmetric, therefore the average and the median are the same. So for the average value you have 50% values below and 50% values above. But you can see, for example, if you take like something like 50, you can see that for normal distribution the probability for 50 will be relatively small. But for the uniform distribution it will be almost 0.2. So we have larger probabilities here and smaller probabilities here for the uniform distribution. Okay. Now let's talk about how to use CDF for example, for calculating the probabilities. Okay, let me start from the following. How many values are, for example, below 60? So if you count all people whose weight is below 60 kilograms, how many values will we get? What's the probability to find a person below 60? Okay, so in this case we know a value and we need to calculate the probability. So we will use the CDF and we will use the normal distribution, P norm. And then the value is 60, and the parameters are the same as we used before. Okay. So and then I can show this value. Okay. So this is the 1.16. So it means that 16% of the values, have weight 60 kilograms or below. Or you can think that the probability. So if you take a random person, the probability from this population, the probability that the weight of this random person will be 60 or below is 16%, exactly 16%. Okay. Now what will be a probability? Let me change it from P to P1. Okay. Now what will be a probability to get a person, random person, and then we select a random person and the weight is 80 or below? Well, it's the same, so we just copy and paste these two lines. So P2 here. And then we change 60 to 80. So the population is the same, the population parameters are the same, we just change the value, okay? So, and if you look at this one, so 80 is here, so the probability should be about 0.8, maybe a little bit larger than 0.8. Well, in fact, it's 0.48 because it's symmetric. So if you look at the 60 and 80, they're symmetric, right? But let's see, let's look at this, okay? So you can see indeed the probability is 0.48, okay? Oh, sorry, the 0.84, okay. Now, what will be the probability to get a value in between 60 and 80? And that's exactly the difference, right? So we take P2 and subtract the P1. So the probability to get the value in between P1, P will be P2 and P1. So it's a probability to get a value equal or below 80 minus the probability to get a value equal or below 60, right? So if you look at this, okay, we got, yeah, I need to run this again, I think. Okay, like this. We got 68.3, right? 68.3, so I will just write it down here, 68.3. You remember that that's one of these properties of normal distribution. 68.3% of values align within one standard deviation of mean. Now look, we have standard deviation 10 and the average is 70, okay? So 60, it's one standard deviation below mean, and 70 and 80 is one standard deviation is above mean. So the 60 and 80, it's exactly one standard deviation of mean. And now we have proven by doing these calculations that indeed if you go one standard deviation from mean in both directions, you will get 68.3% of the values. Okay. Now, how to get, for example, if we take two standard deviations, right? So in this case, we need to take 50 and 90. That's the two standard deviations of mean. So we'll just copy this, copy the 3 lines or 6 lines of code and change 60 to 50 and 80 to 90. Okay. So now that's the probability to get a value below or equal to 50. It's 2.28, something like this. This is the probability to get a value below 90, equal below 90. It's 97.7. And this is the probability to get a value in between. You see, it's 95.5%. Exactly what we have learned in the theoretical part. So it's 95.5% of the values align within 2 standard deviations of mean. Okay. Now you remember that we also have a standardized distribution with average is equal to 0 and standard deviation is equal to 1. You can also use standardized distribution. For example, if you write P1 equal to P norm and, for example, 1, you don't need to specify mu and sigma in this case, because if you don't do that, it assumes that the standard deviation will be 1 and average will be 0. So in this case, I say, give me a probability to get a value below 1 standard deviation of mean. Okay. So and this is the, let me show you this. This is 0.84, okay, so it's 1 standard deviation, it's like we used 80 here. So if I do the same for -1, so -1 standard deviation of mean, and I'll call it P2, okay, P2, so that's the probability, it's 0.16. And then if you write P equal to P2 minus P1 and show P, you will get the same value, you'll get 68.3. I think I need to change the signs to get it correctly, like this. Okay. So you get 68.3% between -1 and +1 standard deviation. So if you take average and go by standard deviation to 1 standard deviation on both sides, you will get 68.3%. So indeed, what we have learned in the theory as the properties of normal distribution, it works. So we can at least using CDF for normal distribution to prove that. Now let's talk about inverse cumulative distribution function. As you remember, inverse function gives a value for a given probability. Okay. For example, you remember that if we take 1/96 standard deviation of means, we will get 95% of most common values. So what it means? It means that if we take average minus 1/96 standard deviation, we should get 0.025, it's 2.5%. And then if we take average plus 196 standard deviations, we should get 0.975. Okay, so we have 95% in between. Let's check that, and I will first of all, I will use the distribution with given parameters mu and sigma, and then I will do the same for standardized distribution. Okay, so let's start with a left tail. Okay, so we know that if we have 95% in between, on both tails we have 5. So it's 2.5 and 2.5, okay? Let's find a value. Let's find a value x. And in this case, I can use Q norm. So it's ICDF for normal distribution. For the probability, 0.25, okay? So 0.025, so it's 2.5% smaller than x, okay? Then I use this mu and sigma, okay? So if I run it and show the value, it will be 50.4. Okay, why 50.4? Well, you can check it. It's exactly, I will just show mu minus sigma times 196. So let's see, that's exactly 50.4. So if you take one standard deviations below the average, the probability to find a value smaller than that or equal is 0.025. So in this case, we know the probability, but we got a value, okay? Now I'll show the same, let me call it x1 here, x1 and x1 here. Then let's do the same for the right tail, right? Q norm 0.974. So we have 2.5% larger than this value, right? So it's a right tail, mu and sigma. And then show x2. So we get 89.6. Okay, so 89.6. Let's check that. Show mu plus sigma times 196. And that's exactly 89.6, right? So it means that 95% of the most common values are located between 50.4 and 89.6 kilograms. Okay, so in this case we know the probabilities, but we don't know the values, and that's how to get them. Okay, now we can use standardized distribution to get actually the same, because if it's standardized distribution, we should get minus 196 and plus 196, right? So let's see that x1 q equal to q norm and 0.025. I don't specify any parameters, because if I don't do that, the function will assume that it's standardized distribution, to the average is 0 and standard deviation is 1. Okay, so let me show the x1. So we get minus 196, exactly what we expected. And then we can do the same with x2, q norm 0.975, and it's show x2, you can see plus 196. So 95% of the values in the normal distribution are located between average minus 196 standard deviations and average plus 196 standard deviations. Okay. Now the fourth function, which allows you to get a random sample from a population with given parameter. Okay, so this is how to get a random value. Get a random value. Okay. So let's say we define a sample size which is 10, and then we say, for example, x equal to r norm. So in this case, I say random value for normal distribution. How many values? N. Then what are parameters? Mu and sigma. So it will use these parameters which we defined before, these ones. So it will use a population, normally distributed population with average 70 and standard deviation 10, and we'll get a number, a random number, in this case 10 random numbers from this population. So let's see what we get. So I'll just show the result. So you can see that that's the 10 values we get. 68.6, 61.9. And you can see that most of the values are somewhere between 50 and 80. Okay. Now what else we can do? We can round the values. So x equal to round x, and then comma 1. What it means? It means round to 1 decimal. So we'll see only 1 decimal after the integer part. So you have seen the values already here. We have like at least 5 decimals here. But if you round them to 1 decimal, you can see a more neat representation of the, if we talk about weight, it's weight, of course. Okay. Now, because R norm is random function, every time you run this, you will get different values. So let me just demonstrate this. I run it and I got 61.4, 67.7 in the first two. Then I run it again, you see the different numbers. Run it again, different numbers. Run it again, different numbers. So it's a very good way of thinking how to get a random sample. So if you want to simulate this procedure, getting a random sample, you can use this function rnorm. Okay. Now let me calculate the statistics of my sample. So I calculate m as a mean of x, and then I calculate s as a standard deviation of x. Okay, so these two functions, mean and sd, gives you mean and standard deviation. And I will show these two functions together, m and s. Now look, I'm going to repeat it several times. You remember that the real average for population is 70 and the real standard deviation is 10. Okay, so look, I've got 67.3 and 12. Then it's 63.7 and 10. Then it's 67.7 and 10, and so on. So sometimes it's above 70, sometimes it's below 70. So it depends on the how many times we try that. Okay. But most of the time you can see that it's pretty close to the real values, but not exactly the same. We will discuss this relationship and how these values depend on the sample size in the next block. So far, you just need to learn how to generate the random numbers. Okay. Now the next point is, you know already how to calculate these parameters. The next point is how to make a cuckoo plot. Okay. The cuckoo plot for normal distribution, you can make it using a function cuckoo norm and your values. So that's the values I've generated last time. Your plot will look a different way because every time we generate random numbers, we get different numbers. Okay. If you want, it's a plot. If you want to, you change the color, for example, color equal to blue. So you can use the same parameters. You can add a grid if you want. Grid. So you can use the same parameters as for the real plots. For example, you can change the points, the symbol for the points, and the size for the points, and so on. If you want, you can also add a theoretical line. So for ideal normal distribution, you can do it by using function cuckoo line, and then the same x. Let me use the red color and the dashed line as I did it in the lectures. So and then you run these 3 lines together. So now you can see, so this is your sample, and this is the ideal theoretical distribution. You can see that even though you took your sample randomly from normal distribution, it doesn't look very close to normal. Okay. You can make a test if it came from normally distributed population by using function Shapiro test. So Shapiro test makes a Shapiro-Wilk test for normality. You only provide your values, and then you can show the results of the test. So let's see what it will be in my case. Again, in your case, it will be different because you will get different numbers. I recommend you to repeat it several times so you can see that sometimes the p-value will be pretty large, but sometimes you will get pretty extreme sample. So look at this. We got p-value 0.16 or 0.17. You can see it here. So it means that 17% chance to get a sample like we have, or even worse, if indeed it came from normally distributed population. And we know it does, okay? So it did. We know that we took random sample from normally distributed population indeed, okay? If you want just to get a p-value, you can use res and then $, you can see a p-value. So this gives you only a p-value without any other statistics, okay? The last 2 things is how to calculate skewness and kurtosis. Unfortunately, R doesn't have these 2 functions implemented in standard R package, so we need to install a special package for that. So let's do that. We go to Packages, click Install. The package you are looking for, it's called Moments. So it's a package that calculates all moments. You remember we have at least 4 moments. The mean is the first moment, standard deviation is the second moment, then we have skewness as the third moment, and kurtosis as the fourth moment. So you just install it. Okay, just wait until it gets installed. So no errors. Now we just use library to get the package to the memory. Moments. Then we can calculate the skewness. I'll just show them skewness for x and the kurtosis for x. So let's see. You remember that skewness should be around 0 if it's symmetrical, and kurtosis should be around 3. So we got. In this case, I got a good skewness. It's around 0 indeed, but the kurtosis is pretty small. So it means that it's wider than it should be. Okay. What I'm going to do, I'm going to select all these lines, including the line where I generate the points. This one. Okay. Now let's repeat it several times. So I run it. Now look, we have a skewness not very good, but the kurtosis is good. Now you can see that indeed the values are skewed, right? So you can see the skewness is not good. And this is the p-value. So the p-value actually tells you it's not from normal distribution. Only 2% chance to get a value from normal distribution like you have, or even worse. But we know it does. It came from normal distribution. Okay. Sometimes you may have some extreme sample. So let's run it again. Now you see we have a good kurtosis and pretty good skewness, and you can see the p-value is 0.9. It's pretty high p-value. So now you don't have any doubts that it came from normal distribution populations. If you look at the cuckoo plot, you can see that most of the values line are pretty close to a straight line. We have one rather extreme value. But indeed, the sample size is small, so it is okay to get extreme value in this case. Okay, and I will run it the 4th time. So again, relatively good skewness, and then the kurtosis is a little bit smaller than 3, but still relatively good. It's a small sample. You will never get exactly 0 and 3. It's almost impossible for this sample size. And you can see that the p-value is pretty large. So 45% chance to get a sample as bad as we have, or even worse if it came from normally distributed population.